the electrons in the conductor are going to move with the wave. That's the way an antenna works with radio waves. You excite the electrons with the frequency of whatever's coming in, and you can then read that out to receive the signal, or you can transmit it again to propagate that signal elsewhere. But when you excite the electrons, you are imparting energy into the motion of electrons. That energy comes out of the incident beam, and therefore the incident beam is attenuated. So conduction electrons do that. Phonons do that, particularly optical phonons. If you excite the vibration of ions in the material, you are again depositing energy in optical phonons, and that energy is taken out of the incident beam. Finally, there are electronic transitions. If my beam comes in and it can couple to the valence electrons, for example, and excite them away from the atom, or if it can couple to the core electrons and cause them to transition into higher energy states, then those are also energy absorption mechanisms, and those will contribute to the attenuation. So all of these absorption mechanisms contribute to the attenuation, and in particularly in the case of metals, where we're exciting conduction electrons, this can make the attenuation coefficient so high that the penetration of the light beam into the solid is very, very short, and therefore the metals are opaque. Insulator semiconductor. Did I record to do Rayleigh scattering? Yeah, I'm going to do Rayleigh scattering before I go back to that. Got the slides out of order, I think. The other thing that will cause a beam to attenuate is incoherent scattering, where I have things in the material that cause the beam of light to be scattered away. Any intensity that is scattered out of the beam is no longer available for the transmitted beam, and therefore the intensity of the transmitted beam decreases as we get this Rayleigh scattering. Sources of Rayleigh scattering, well, anything that changes the homogeneity of the glass will change the Rayleigh scattering. Density fluctuations, chemical heterogeneities, defects, second phase particles. You know, the biblical now I see is through a glass darkly. Well, until fairly recently, nobody knew how to make glass that was very transparent. So you would always see through a glass kind of darkly because you didn't have very good quality glass. Even today, I pick up just a relatively cheap, particularly one of those drink glasses that has a very thick bottom, and look through the bottom. You'll see the image distorted. There'll be clearly not full transmission mainly because of the density fluctuations inside the glass, which are doing Rayleigh scattering and knocking out the intensity. In fact, in my mind, the most beautiful material object in the whole world, and there are people like Steuben who know how to make them, is a big, thick, absolutely perfect piece of glass, which has absolute optical clarity. I don't know if you've ever had the opportunity to see one and look through it, but they're really amazingly beautiful. Of course, they'll use dopants to give them a slightly off clear color, maybe a blue tinge, but a thick piece of glass that is absolutely perfect is an amazingly beautiful object. But to do that, you have to get rid of the density fluctuations, the chemical heterogeneities, the defects in secondary particles, so that you can get rid of Rayleigh attenuation. Let me go back to absorption since I've covered the two. To talk about absorption in an insulator or semiconductor, and this is actually maybe better to talk about in terms of particles. But if we look at the electromagnetic spectrum, and we imagine the electromagnetic spectrum being shot through or onto a typical semiconductor, which has its band gap in the ultraviolet, a little bit beyond the visible region, so it is transparent, semiconductor insulator, then the absorption spectrum will look something like this. A microwave will not have much effect on a semiconductor insulator because you don't really have free charges to move. There'll be some absorption, but not a lot. When you get up into the infrared region, then you begin to have frequencies that can couple to the optical phonons. And in infrared, it's mainly the optical phonons that will cause the absorption. Coming up a little higher, you may, toward the end of the infrared and the visible, is where you begin to see ionic transitions. I have a semiconductor, the semiconductor is ordinarily made of ions, and the electrons and the ions can undergo transitions between various possible electron states. And those will provide absorption bands, usually often around the visible, which is the reason we use ions to color glass, because these absorptions will let us put different colors into the glass. Eventually, we get to a frequency that's high enough to excite electrons across the band gap. And at that point, this is an insulator here because the band gap is out in the ultraviolet. At that point, the material becomes opaque. No longer will light go through it at all because it will be absorbed by transitions across the band gap. It remains opaque until we get to a still higher energy, at which the frequency becomes too high for these excitations. The excitations, in order to excite, I have to be exciting at a frequency that the electrons can respond. If I get to frequencies beyond where the electrons can respond, the material becomes transparent again. I then have a region of transparency that lasts up into the X-ray region. When I get to electromagnetic waves all up in the X-ray region, then I'm getting to packets of energy in the electron waves that can excite electronic transitions within the atoms. When I excite electronic transitions within the atoms, I get discrete absorption peaks that are associated with these atomic transitions. And it's these discrete absorption peaks, very sharp ones, that let me use things like X-rays to do chemical analysis. Since the pattern of these peaks is characteristic of the material, I can look at X-ray absorptions and use that to analyze the chemical content of the material. The frequencies of these peaks tell me what elements are present. The intensities of these peaks, the intensities of the absorption, will tell me how much of an element is present. So if you ask how it is that astronomers know very precisely the composition of some star that's 50 light years away, all they have to do is look at spectra, see the peaks that are absorbed and emitted, and in that way characterize the composition of the material. We use this all the time in material science and X-ray techniques, X-ray spectroscopies to determine the compositions of materials. Actually, we more frequently use electrons rather than X-ray, but the same principle. You get these core transitions, the transitions of core electrons from one state to another. You have characteristic frequencies. The frequencies tell you which elements are present. The intensities tell you how much. So you can do a rather accurate chemical analysis of just about anything you want in a decent scanning electron microscope by just plugging in an energy dispersive X-ray monitor and looking at the spectrum. Diffraction. The final thing that we get from waves are diffraction, which is historically enormously important because as recently as the late 19th century, people did not know that most materials were crystalline. They were discovered to be crystalline, and their crystalline structures were sorted out by observing that these materials gave rise to discrete diffraction peaks when bombarded with X-rays, and that told us that they had to have regular atomic arrangements. What happens is the following results in Bagg's law. Suppose we fire a beam of X-rays with a certain wavelength toward a material that has a regular structure. If the material has a regular structure, its atoms are arranged in planes with respect to this beam, and we can assume they're continuous planes even if they're made up of individual atoms. As the X-rays come into the material, some of them are reflected, and some of the X-ray intensity is transmitted. If in general, the X-rays that are reflected from these different planes will be out of phase with one another. If they're out of phase with one another, if they don't reinforce when they meet out here in space, they'll cancel out. You don't see anything. If, however, the angle is such that the distance between these planes just gives us an integral number of wavelengths in these scattered waves, then they will reinforce. If they reinforce, we get a good strong beam coming out at the particular angle that provides this reinforcement. By observing the angles at which we see these diffraction peaks, we can determine how far apart planes of atoms are. The Bragg condition, n times the wavelength lambda, n is just an integer in this case, is equal to 2d sine theta. We know our wavelength. We measure the angles at which these diffraction peaks are emitted, and that tells us the distances between the atomic planes. If we look at a whole series of such diffraction peaks, that gives us all of the distances that we can find in the material, all the interplanar distances that are there. Putting together the different interplanar differences, we can infer what the atomic structure of the material is. Well, I said that a bit too strongly. You can identify a group of structures that it might have. And in simple crystal structures, this becomes fairly obvious. If I'm going to determine that something's face center cubic or body center cubic or distinguish them, if I know it has a fairly simple structure, it's easy to distinguish and determine its structure by looking at the diffraction pattern. You also use the diffraction pattern to, for example, to try to find the structures of complex organic molecules, like the original interpretation of the structure of DNA. The way you would do that is to crystallize them, determine the crystal structure by X-ray diffraction, and then from that determine what the atomic structure has to be. The problem is, when you get very complicated unit cells, as you would have in the crystallization of a complex molecule, is that the diffraction pattern does not have a unique inverse. You can't look at the diffraction pattern and say there's one and only one structure that this complex molecule can have. If the molecule is complex, it can in fact have a number of structures. They're a discrete number of structures, but it could have a number of different structures. And so still to this day, there are people who I think of, knowing well when I'm drawing a blank on his name over in the chemistry department, who to this day his specialty is X-ray determinations of the structures of complex molecules. And there's a real challenge over there in taking the diffraction pattern. First you have to crystallize complex molecules. You then take the diffraction pattern, and then you try to back calculate from the diffraction pattern the various structures that would be compatible with that diffraction pattern. Then you have to bring in other pieces of information, what you know about the bonding configurations and so on, to infer what the actual structure is. For example, when Rosa, I'm just still drawing a blank on her name, made the breakthrough on DNA of crystallizing and getting a diffraction pattern, which made it absolutely inevitable that before long someone was going to come up with the right structure. The diffraction pattern in and of itself was not enough because it was not unique. There would be a number of structures that would be consistent with that diffraction pattern. And the contribution that Crick and Watson made was to choose that particular structure, which made the most sense, consistent with the diffraction pattern, and also checked out on all the other ways they had of analyzing what the diffraction pattern was. So that's the diffraction pattern. We actually use I'm cheating here because we tend to use electrons more than X-rays, and they're not electromagnetic waves, but this just gives you, shows how you use diffraction. This happens to be a transmission electron micrograph of a piece of structural steel that contains two different phases, the high temperature FCC and the low temperature BCC structure. This is what's called a bright field electron micrograph. Here's the diffraction pattern showing you discrete spots. Here's an index of the diffraction pattern that shows you that two different structures are present. We know there's supposed to be FCC and BCC, so we can pull that out quite easily. You can then do, and you can do this with X-rays too, what's called a dark field. You can put your detector right on one of these spots, in which case the phase or structure associated with that spot will light up, and the other will remain dark. So in this bright field, turns out there's a mixture of the two phases. Here we've used a face center cubic spot to light up the FCC material, and all the stuff that lights up white is face center cubic material in the BCC matrix. So you can do an awful lot in real time with this with diffraction information, and we certainly, that's a core of materials characterization. Exploding light as a wave, optical fibers, greenhouses, and solar heaters are the things I'll talk about. Optical fibers. The problem with an optical fiber is that no optical fiber is infinitely thin. As a consequence, if we take a piece of glass, we will have a dispersion, a loss of our signal, in that if we put the light in at this end, some of the rays of light will go straight down the axis of the fiber. So they'll arrive at this other end at one time. Other of those rays will go to the edge of the fiber and bounce back. So in a perfectly uniform piece of glass, they will arrive at this end at a slightly later time. That was a problem that was addressed. Let me take a step back before I get to that. Optical fibers hit for communication in kind of the mid-'80s is when they really took off. Mainly work done at Bell Labs and a few other places, and then the manufacture of them at places like Corning. And it really was a triumph of material science because of all the things you had to do. To get a good optical fiber, you have to have a very small diameter to minimize the surface losses, because anything that comes in at too high an angle is going to be lost to space. You have to have a perfect cylinder, almost dead-on perfect cylinder to minimize surface scattering. If there's any roughness here, it's going to scatter the light, and that's going to mess up your signal. You have to have exceptional purity to suppress absorption and exceptional uniformity to suppress radio scattering. There was a space of about, the better part of a decade, from the 70s through the 80s, in which ceramists working on this problem were able to provide 3 to 4 orders of magnitude improvement in both the purity and dimensional tolerance of glass, and to do it in a way that could be manufactured in hundreds of miles. And that was the breakthrough that made optical fibers possible. And it was a real triumph of people at Corning and other places. The next sophistication, I jumped ahead of myself, was the gradient fiber. I remember first hearing about this. A guy named Chuck Kirchin at Bell Labs was one of the real inventors of gradient fibers. And I couldn't quite figure out how these things worked. So he was out here at a conference. So he and I went over to that time. Larry Blake's ran kind of a jazz club late at night. So we went over there, pitch dark, drinking beer, and on the back of a napkin, Chuck showed me how these things worked. And so I actually walked into an E45 lecture the next day with a napkin to discuss that subject. I no longer have a napkin. It's really pretty simple. What you would like to do is to arrange things so that whatever path the ray takes in getting from one end of the fiber to another, it takes exactly the same time. You use the fact that as the index of refraction goes down, the light travels faster. So let me take this tiny little cylinder and let me go one further level of sophistication and dope that cylinder with chemicals that change the index of refraction. Easy to find stuff that will raise the index of refraction. So we take the center of the cylinder, that's where the concentration is highest. As we go out to the edge, we let the concentration tail off. So we have a gradient in chemical composition going from the center to the edge. And that gradient is tuned so that whatever path this ray of light takes, it takes essentially the same time to travel a certain distance. If it goes out to the edge, it's traveling faster. If it goes down the center, it's traveling slower, so the two rays get here at the same time. Well, perfection is beyond human capability, but they did an awfully good job with this. And that's the essence of the really high-quality light fibers now. I should also mention that, in fact, I've got this kind of homework. Put on a final exam years ago in a class of 300. I think only surprisingly few people got it right. But if you look at optical fibers these days, one of the things that will surprise you is you can't see through them. They are as opaque as can be. The reason is that the light that we use in optical fibers is not visible light. It tends to be infrared, usually with gallium arsenide lasers of one kind or another. And therefore, you don't care whether your fiber is optical in the visible range. You never use that. You want it to be transparent in the infrared frequency at which you're emitting the laser light. So you pick up optical fibers that are used to transmit information, and the first thing you notice about them, they look like metal wires rather than like optical fibers. The greenhouse effect, let me get this out and I'll finish up with this today. Solar energy is really an old thing. One good example, if you go to Paris, you'll obviously go to see the Louvre. You go down the Champs-Elysees, you march over toward the Louvre, past the obelisk there, the Place de Concorde, and on your right, you will see a greenhouse called Orangerie. It was put up by Louis the something or another, 14th maybe, and its purpose was so they could grow fruits for the royal table in the middle of the winter in Paris. If you go to Boston, for example, in the Back Bay, the old houses, the rich old ones, they have solaria kind of on the roof. Greenhouses, if you want, where people go in the wintertime and enjoy the sunlight and the natural heating of the sun. So greenhouses have been around for a long time. And what they basically are solar energy devices, and how do they work? It's really very simple. Suppose that we have here a piece of glass. And suppose we have chosen that piece of glass so that it is transparent to visible light. Very little absorption here where visible light is. But suppose that we've chosen that glass so that it's very absorbent down here in the infrared. If we take a glass window pane and behind it put a black object or dark object, like dark dirt or black would be even better. If it's a dark object, then what that's telling you is it doesn't reflect visible light. It absorbs visible light. It's going to emit it at some lower frequency, so it's going to put that light back out in the infrared. So the light comes through the pane, hits the back, and comes back out in the infrared. If I have chosen a piece of glass, and the long history of greenhouses tell you it's not hard to do, just natural glass, which is transparent to visible light and opaque in the infrared, you've got the Hotel California. You can get in, but you can't get out. And as a consequence, all of the radiation that comes through that glass, well, not all, of course, but a vast fraction of it, gets trapped right back here. Which means that just in ordinary sunlight, with a piece of glass and a black background, you have a perfectly efficient solar heater. You can use it to grow fruits in the wintertime, to sunbathe in your solarium in the wintertime when it's below zero outside, and this is very effective. And of course, this is the same way that we make, with more sophistication, we make solar hot water heaters, and so basically this way today. We have a pane that lets in the sunlight, traps the heat. There's a black thing behind here and some water in between that gets heated. You've got a solar water heater. So this is the way a solarium essentially works. And it's very simple. It's been around for generations, and we made some improvements, but frankly, the engineering is not all that different than it was in the 1700s when the Orangerie was made in Paris. Okay, we still have to talk about all the wonderful things we can do with light as a particle, and we will do that on Monday. I'll see you then.